This meeting is being recorded.
Today, I am going to discuss cryogenic distillation, Part 1. Distillation, as you know, it is a process of separating components from a homogeneous solution by partial vaporization. This one is cryogenic distillation. That means distillation will be carried out at very low temperature. Low temperature means lower than 150 degrees Celsius. That is the starting point of cryogenic temperature because as per National Bureau of Standard, with the help of normal refrigeration process, we can go up to minus 150 degrees Celsius, not beyond that. And cryogenic can go beyond that, and it can reach up to even absolute temperature, though we have not yet reached absolute temperature. Uh, with respect to separation of oxygen and nitrogen from air, air is a mixture primarily of oxygen and nitrogen. Roughly, we can say 79% nitrogen and 21% oxygen. Though there are some other trace components, one major component that is there in percent level is the argon. Argon concentration in air is about 1%. So by cryogenic distillation process also, sometimes we can separate argon as an byproduct. Let me discuss this thing in details. So separation of nitrogen and oxygen from air is a very important application of cryogenic distillation. Both nitrogen and oxygen have lots of industrial and medical uses. They can be used both in liquid and gaseous forms. And as I already mentioned, cryogenic distillation means distillation at very low temperature, that is lower than or below minus 150 degrees Celsius. So air is liquefied before feeding into distillation column. So heat exchanger plays a very important role here, and as such, we call this distillation unit along with that heat exchanger uh, as cold box. So that I'll be discussing. Uh, Now, one important thing all of you should know, if we need oxygen and nitrogen in gaseous form, there is another technology which is known as pressure swing adsorption or vacuum swing adsorption. So with the help of that process, we can separate oxygen and nitrogen from air. There we need not do liquefaction, and this process is very competitive. So for small to medium scale application, we can uh, apply this particular process. And only one thing that we should keep in mind, that the purity level, if we want to get high purity oxygen or high purity nitrogen, then obviously cryogenic distillation is better option. Now here I have shown a typical Linde double column air liquefaction and purification system. Here there are two columns. One is at the top and another one is at the bottom. They are joined together with the help of this section. This section is known as condenser reboiler. Condenser reboiler, that means this particular unit will be acting both as condenser as well as reboiler. So in this section, when it will be condensing uh, nitrogen in the liquid form and vaporizing oxygen. So this will be when it will be vaporizing liquid oxygen to vapor oxygen, that will be acting as reboiler. But when it will be condensing nitrogen to liquid nitrogen, it will be acting as condenser. So this unit is known as condenser reboiler. Here in this bottom section, of course, we are having a unit similar to reboiler. So here, let me show you the flow, how air is liquefied, then it is fractionated. So after compression of this air to very high pressure, say 20 megapascal or so, temperature of air increases. So it is that temperature is lowered by extracting heat with this cold fluid stream in this heat exchanger. So temperature of air will be going down, then that high pressure, low temperature air will be passing through this reboiler. This temperature of this liquid air is low, so temperature of this air will be lowered further, and that high pressure air at this temperature will be expanded using this expansion valve. So this air will be, when it will be expanded, part of this will be liquefied and part of this will remain as vapor. That vapor fraction will go up, that will be interacted with the liquid nitrogen which is flowing down. So the purity of that vapor is mostly nitrogen, so that will be increased, and after condensation we will be getting liquid nitrogen here. And a liquid portion of the air, mostly oxygen, that will be actually some part of it is nitrogen. That nitrogen will be stripped off with the vapor which will be coming out from this liquid. So that nitrogen will be going up. So the liquid which is flowing down, that will be gradually enriched with oxygen. So that will be going down. So we will be getting nitrogen here. And this particular liquid air where purity of oxygen is high, that will be again expanded with this expansion valve, and due to that, part of it will becomes liquid that will be flowing down, and part of it will be vapor that will be nitrogen, so that will be going up. And little amount of oxygen that will be there, that will be rectified with the help of this liquid nitrogen which is flowing down. So in the top section of this column, we will be getting pure nitrogen, so nitrogen gas. So if we want to get nitrogen gas as product, so that we can get from here. And if we want to get oxygen gas, then that vapor which is coming out from liquid oxygen, that from there we can get gaseous oxygen. So here we can see that all the form of oxygen and nitrogen, that is gaseous oxygen and gaseous nitrogen we can get from here, and liquid oxygen and liquid nitrogen we can get from here. So this is the cryogenic distillation process where we can get all form of cryogenic product. So here I have shown one that air separation and purification unit. This is a rectangular shaped column. So this is particularly known as cold box. From this cold box, we get all types of products. Another view of the cryogenic distillation column is this one, cylindrical one, this one. Here also, we get all sorts of products from this cold box. Before showing another view, let me show the one view of the heat exchanger. As heat exchanger is very, very important part of this cryogenic distillation process. This heat exchanger should have very, very high efficiency. Effectiveness factor should be more than 0.95, 96. If it is 0.99 or 1, then it is better. Particularly this heat exchanger is having very high surface area. Fin tubes are generally used to extend the surface area of heat exchanger. Fin tube heat exchanger, then Collins coil tube heat exchangers. So different matrix heat exchangers. So all sorts of heat exchangers are used in cryogenic process. They are having very high effectiveness factor. So here I have shown that particular cold box where air separation and purification unit lies. Here, in addition to that, I have shown two storage tank, cryogenic storage tank. One is for liquid oxygen and another one is for the liquid nitrogen. And now I will be showing the distillation columns. This is internals of the distillation columns have been shown. Now, one important thing I want to mention, distillation columns may be pack type columns or plate type columns. Both pack types and plate types, and nowadays hybrid columns are also there, can be used for chemical separation purpose. But for cryogenic distillation, generally plate columns are used. The main reason of using plate columns is that it is having more flexibility, more adaptability at cryogenic temperature, whereas packing materials are not very adaptable in at this low temperature uh, uh, operation. The main reason is that sometimes due to this thermal shock, there may be uh, crushing or damage of the packing materials. Due to that, the properties may change. So that's why we generally use plate types distillation columns in cryogenic distillation process. Here, three types of plates have been shown. One is sieve tray. You can see the perforations there in the sieve trays. They are having about 2 to 3 millimeter in diameter or even less. So here, this main advantage of the sieve tray is that it is very easy to construct and less costly. But main disadvantage of this sieve tray is that some problem of distillation columns like flooding, loading, weeping, dripping, that type of problems may be more in sieve tray. compared to bubble cap and valve tray. Bubble cap is uh, I mean to say efficiency wise, flexibility wise, it is the best out of these three. But the main disadvantage of this bubble cap tray is that it is costly, very, very costly, and not easy to manufacture. Uh, uh, Due to that, where it is not necessary absolutely, there it is not used. Otherwise, if we want to have more flexibility, more efficiency, more turn down ratio, out of all these three, this one is having maximum turn down ratio. So a bubble cap, you see, when vapor will be flowing through this liquid level, then that vapor has to travel all the way through this path. That means initially it has to go up, then again it has to turn around, then come down, then again take another U-turn and come up. So here the interaction time, residence time, or interaction time between vapor and liquid is more. That's why here mass transfer will be achieved to maximum extent. Whereas in this half tray, you can see here it is represented in this way. That means when the pressure in the bottom section of the tray is high, then this valve will be opening and vapor will be bubbling through. And when pressure is low, it will be closing. So liquid cannot flow down. So weeping and other types of problem is less compared to sip tray here. So this is also advantageous, but as per uh, turn down ratio is concerned, it is having turn down ratio in between these two. That is, bubble cap tray is having maximum turn down ratio, then valve tray, then sip tray. Now we'll be doing design of this distillation column. Design means we are going to determine number of plates or tray inside the distillation column. We will be using initially McKeppthily method. It is for binary solution we will be using, as air is a binary mixture of nitrogen and oxygen. So it is the ideal example of using McKeppthily method. It is stage by stage calculation process based on the assumption of constant molar overflow. So McKeppthily actually assumed this, and the meaning of this constant molar overflow, as in the distillation column, there are two sections, rectification section and stripping section. So liquid flow rate in rectification section is constant in all stages, all trace to trace. Liquid flow rate is same. Similarly, vapor flow rate is also same. They are not changing, constant. Whereas in the stripping section also, liquid flow rate and vapor flow rate are constant. But the liquid flow rate in stripping section and liquid flow rate in rectification section, they are not same. Vapor flow rate are also not same, because feed is entering and that is contributing some portion of vapor and liquid in each section. So due to this assumption, that is constant molar overflow, due to this we have to lance down these four conclusion. First one is that two components have equal and constant enthalpies of vaporization, which is very difficult to realize or believe. This is one point of criticism of McKeith method. And second conclusion is that heat capacity changes are negligible compared to heat of vaporization. To some extent, this we can consider, but of course, in some cases, it may differ. And then third and fourth conclusion, the column is well insulated, so heat loss is negligible. We can believe that, and the pressure in the column is uniform. More or less we can, but at the bottom section, low pressure is high compared to top section, but we may assume this one is uniform. So these conditions leads to the conditions of constant molar overflow. Now, McKeith method, design method, that is determining the number of trays or number of ideal stages uh, that is calculated based on using the concept of operating lines and equilibrium curves. So first of all, let us understand what is operating lines and how it differs from equilibrium lines. Operating lines relates the composition of one specific component. Generally in distillation, we refer more volatile component, say A, between two interacting streams. So when liquid is coming from top and vapor is coming from bottom of a tray and they are interacting with each other, mass transfer is taking place, and after interaction they are separated out. So during this interaction stage, the relationship between the composition of the liquid and composition of the vapor, that is given by the operating line equation. Whereas the equilibrium lines relates the composition of the same component between two leaving or outgoing streams after interaction and attaining chemical equilibrium. The operating lines are obtained from mass or material balance equations. They are straight lines on molar basis if equimolar overflow assumption is made. So if we use McKeith method, then we will be having all these operating lines as straight line. We are having three operating lines for rectification section, operating lines for sweeping section, and operating line for the feed conditions. Now, let us discuss something about vapor-liquid equilibria data. The ratio of yi by xi occurs so frequently in separation discussions that this ratio is defined either as equilibrium constant ki or the distribution coefficient ki, or the separation factor of the component I. So Ki is defined like this. So if we replace by pressure expression, then it is nothing but Pi naught by Pt, total pressure. And this is vapor pressure. So a more useful term, which is less temperature dependent, but still relates the ease of separation of two components, is known as the relative volatility, and is defined as alpha 1, 2. That means relative volatility of 2 with respect to 1. That is ratio of K1 by K2. So if we replace by mole fraction, then we will be getting Y1 by X1 and Y2 by X2. Now Y2 and X2, if we replace by y1 and x2, it will take the form of this. Because as it is binary mixture, x1, x2 is equals to 1 and y1, y2 equals to 1. So that's why we can replace x2 and y2 by this way. We will be getting relative volatility as this. And with respect to distribution coefficient also, we can get this expression for x1 and x2. Now, we'll be finding out operating lines for the rectification section. So based on the envelope that is drawn here, we'll be doing material balance or mass balance. So as it is equimolar overflow, all the vapor flow rates in the rectification section are constant, and that is taken as V, and all the liquid flow rates in this rectification section is constant, that is taken as L. And here one important thing that I want to mention, the convention of this composition of these streams. Here you can see there are two streams entering in this particular plate number 1. Plate number here, it is numbered from top. So first plate is plate number 1, second plate, plate number 2, 3, and so on. Now here, with respect to plate number 1, you can see there are two streams entering. This one is liquid and this one is vapor. And two streams are going out. This is vapor and this is liquid. So streams are stream compositions are given based on the tray from which they are coming out or they are leaving. So this particular vapor is leaving plate number 1. That's why its composition is Y1. And this particular stream, that is liquid stream, is leaving this plate number 1. So the composition of this liquid is X1. Accordingly, all the stream number is given. And based on this, we are having this vapor which is entering is yn plus 1, and the composition of this liquid which is leaving this envelope is xn. So now let us do material balance and component balance. So based on that, we will be getting vapor flow rate multiplied by vapor composition. So that total moles of more volatile component which is going upward direction along with this vapor is this one, that will be equals to liquid flow rate into mole fraction of more volatile component in that liquid plus D is the distillate rate into XD, mole fraction of the more volatile component in the distillate. So this way, after rearranging, we are getting Yn plus 1 is equals to L by V into Xn plus D by V into XD. So now if we just modify this L by V in this way, V, that vapor is nothing but liquid flow rate plus distillate flow rate. After little modification, we can write this way, L by D divided by L by D plus 1. This L by D is known as reflux ratio or external reflux ratio R. So we can replace this by R plus 1. So it will be, you can see that this equation will be like y equals to mx plus c. That means it is the equation of a straight line because this slope is constant, and this is also constant for a particular distillation operation. So y equals to mx plus c. So this will give the equation of a straight line, and one more thing, that this particular line will be passing through the point xd. So one point is here on this diagonal line. This is equilibrium curve. The diagonal line, this particular point is xd point. So that operating line of the stripping section, rectification section, we can draw from this point, either using the slope of this operating line like this, or using the intercept, y-intercept of this operating line. So based on that, we can draw this operating line. Next, similarly, for the stripping section also, by drawing this envelope, we can do material balance and we can get operating line equation. Here, one difference is that here liquid flow rate we will be using another notation, L bar, and vapor flow rate by V bar. So, and this is bottom flow rate. So based on that, if we do material balance, we will be getting material balance for the high volatile component. We will be getting similar equation, similar type of equation. And this is, here also you can see this ratio L by V is constant for a particular distillation operation. And this one is also constant for particular distillation operation. So here, this is also a equation of a straight line with negative intercept. So, and this line will be passing through the point XB, that is purity of the bottom product. So, if we demark that XB point on the diagonal line, and if we can determine the slope, then we can draw the operating line for the stripping section. And the number of equilibrium stages we can determine in the stripping section by drawing a vertical line from this point, then horizontal line, vertical line up to equilibrium curve, then horizontal line up to operating line, and so on. This way, number of vertical lines that we will be drawing, that will be number of equilibrium stages. Why it will be so, that I will be discussing in next part, of course. So this is the summary. Cryogenic distillations of oxygen and nitrogen from air was discussed. A typical double column binary distillation configuration was demonstrated. Definition of constant molar overflow and reflux ratio were also given with explanation. Differences between equilibrium curve and operating lines and their interconnectivity for determining number of stages were explained. The equilibrium curve, diagonal line, and operating lines were plotted in order to find out number of equilibrium stages or ideal plates or trays and the location of the feed tray. Next lecture will continue our discussions of binary distillations of air separation using McKinley method with the different feed conditions. Thank you.